Yesterday, I showed you a couple of videos that illustrated a new principle for us. That principle was called the law of conservation of momentum. We said, after watching those videos and analyzing them a little bit, we said yesterday that in an isolated system, momentum will always stay the same. That is, if we account for all the momentum of all the objects within the system. Before we go any further, does anybody remember what an isolated system was? No external forces, right. In an isolated system, that is a system where we have no external forces, no forces like wind, no forces like friction, and so on. We have no external forces. The total momentum will remain constant. You're not going to lose, you're not going to gain. In other words, momentum is conserved. Now, we learned last week impulse, which is the change in momentum, occurs as a result of collisions and other interactions and so on. How do we reconcile the fact that we have momentum always remaining constant with the fact that momentum changes? Well, when we analyze an individual object, there is a change in momentum, a gain or a loss. But when we analyze the system, the total will remain the same. So if two objects collide, one object will gain momentum. One object will lose momentum. The total amount of momentum will remain the same. In one of the videos that we showed you yesterday, the person firing the rifle, holding it out in front of their face, right? The interaction was the bullet being fired. The total momentum before the bullet was fired was 0. The total momentum after it was fired was 0. Well, that's because the bullet gained momentum. It had a momentum of, let's say, 20 forwards, but the gun lost, or you could say gained momentum in the opposite direction, to have a negative 20. 20 plus negative 20 gives me 0. The total momentum still remained the same. There was an impulse for both of them, but the total momentum remained the same. That is, again, if we have an isolated system with no external forces. This is useful when we're talking about interactions such as collisions or explosions, like we saw yesterday, right? We saw two different videos yesterday that illustrated both of these. The first one was an explosion, or something like an explosion. The bullet is being fired from the gun. The second one that we saw was Mel Gibson being hit with this shot from a shotgun and then being propelled back into the plate glass window. We could analyze both of those situations, the explosion or the collision, with this new law that we're learning called the law of conservation of momentum. That is, if we have an isolated system and if we account for the momentum of all of the objects within the system, not just one. If we use one object, then it's impulse. If we use all of the objects, then it's conservation of momentum. And just a little note at the bottom here, just to remind you that, yeah, okay, we can have a change in momentum, that's impulse, when we're analyzing individual objects. But again, if we analyze the system, the whole system, then the total momentum is going to remain the same. You guys might remember when we derived the equation for impulse that we use Newton's second law, F is equal to m times a. Remember I told you, you didn't have to derive the equation. You won't ever have to do that on a test. But you did have to remember that impulse came from Newton's second law, F is equal to m times a. Well, the law of conservation of momentum comes from Newton's third law. We're going to derive this as well. But again, you're not going to have to derive it. You're just going to have to be able to remember that it comes from Newton's third law. You guys remember what Newton's third law is? Mary, it looked like your head was going up there, no? No? What is it, Bruce? Sorry? Yeah, you could say for every action, there's an equal and opposite reaction. If you had me in physics 20, you know that I don't really like saying it that way. I like saying it, if object A applies a force on B, object B applies an equal and opposite force on A. Okay? But every action, there's an equal and opposite reaction is correct. It's just I don't think it's as good a way of saying it. So let's write that down. Let's say F12 is equal to negative F21. That means if object 1 applies a force on object 2 applies an equal but opposite, hence the negative force on number 1. We're going to replace F12 with MA. The mass of object 2 times the acceleration of object 2 equals negative mass of object 1 times the acceleration of object 1. And again, copy this down, but you don't need to be able to regurgitate this. You just need to be able to remember that it comes from Newton's third law. I think the value of writing this down is that it will help you to remember not necessarily the details of the derivation, but it'll help you to remember that it came from Newton's third law. You're more likely to be able to picture this in your notes when the time comes that you're asked that question. Where does it come from? Okay, let's replace A with delta V over delta T. So we got M times delta V over delta T equals negative M1 times delta V1 over delta T1. With me so far? I'm going to cancel out the times. How come I can do that? One says delta T1, one says delta T2. Why can I cancel out those times? Don't they usually have to be the same one? Don't they always have to be the same one to cancel? What do we know about the values of delta T1 and delta T2? If object 1 collides with object 2 for 3 seconds, then object 2 collides with object 1 for 3 seconds. So it's the same value. Different variable, but it's the same value. That leaves me with M2 delta V2 equals negative M1 times delta V1. Look, the impulse gained by number 2 is equal and opposite to the impulse of number 1. But I'm just going to rearrange that a little bit here now. Say M times V2, that's M2, times V2F minus V2I. Right, that's delta V for object 2 equals negative M times V1F minus V1I. So M times delta V becomes M times VF minus VI. If we distribute the M's, we get M2 V2F minus M2 V2I equals negative M1 V1F. Negative times a negative is a plus, M1 V1I. And if I change the order of that, then I end up getting this. M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. Just swapping the order of them around a little bit. What does this tell us? Seriously, what does this tell us? The momentum of object 1 plus the momentum of object 2 initial. In other words, the total initial momentum, we'll say PI, equals M1 V1F plus M2 V2F, the total final momentum. We'll call it PF. This is the law of conservation of momentum, right? In an isolated system where we have no external forces, the total initial momentum will equal the total final momentum. Momentum is conserved. You don't gain or lose as a system, right? We're looking at the whole system here, right? Both objects within the system. If we look individually at object 1, there was a gain of momentum. If we look individually at object 2, there was a loss of momentum. But in the system, the total momentum will remain the same. All right, the best way to do this is to get right into it. We got example number 1 that's on the sheet that I handed out to you a few minutes ago. It says a 1,500 kilogram car traveling north at 20 meters per second collides with a 1,700 kilogram car traveling south at 21 meters per second. I'm going to circle this right away because we've got one car going north, one car going south. Something's got to be negative, right? It doesn't really matter which one is which, but probably make the south negative. The two cars entangle after the collision. What does that mean? They entangle. What does that word entangle mean? Sorry? There's a crash, yeah, but they become one, yeah. Sometimes you can have a car crash and the two cars involved go off in different directions, but sometimes they kind of go off as one because some metal kind of gets twisted together or something like that, right? That's what's happening here. They head off as one. We want to determine the velocity of the wreckage immediately after the collision. The reason we say immediately after the collision as opposed to like 5 seconds later is because if we look at immediately after, then we haven't given friction or other forces a chance to act. Right? If we look at 5 seconds after the crash, frictions definitely come into play here. And what's the problem if frictions had a chance to come into play? Yep. It's not isolated, right? Because we have an external force. So we're looking at just after the collision takes place so that we can treat it as an isolated system and therefore use the law of conservation of momentum. I'm going to say M1 is 1,500 kilograms. I'm going to say M2 is 1,700 kilograms. I'm going to say, this gets a little cumbersome with our subscripts here. I'm going to say V1I, V1, right, object number 1, initial, is 20 meters per second. I'm going to say V2I, object number 2, the 1,700 kilogram car, initial is, what's that going to be? 21? Negative 21 meters per second, right. I'm not going to forget that negative because I circled the south to remind me that I've got to remember that. Two cars in tango head off as one after the collision. What's the velocity of the wreckage immediately after? Listen, I'm just going to call the final velocity VF. I'm not going to call it V1F. I'm not going to call it V2F. How come? Because there's only one object, right? There was two objects before the collision took place, but there's only one object after it takes place. I don't need to bother separating the velocities because of that. So using the law of conservation of momentum, analyzing the system, remember, impulse is valid here. These cars both experience an impulse, but if I'm going to use impulse, I got to pick either car 1 or car 2 to analyze, not both. And that ends up not being the most efficient way to solve this problem. I'm going to say M1 V1I plus M2 V2I. I got two objects, each with a momentum of mv before the collision. What do you think my term is going to be for after the collision? How many objects do I have? Martin? One. So I'm just going to call it mvf. One object with one mass and one velocity. If they bounced apart, that would be fine. I just say M1 V1F plus M2 V2F instead of MVF. Two objects, two terms. One object, one term. Now we start subbing some numbers in here. 1,500 kilograms times V1I is 20 meters per second, plus 1,700 kilograms times negative 21. I've told you guys about that first written response test that you're going to get. You're going to get a question on that first written response question almost identical to this, including opposite directions. One's going north, one's going south. Positive 20, negative 21. What are you going to do for M? Let's add them together. It's one object now that has a mass of 3,200 kilograms. Times VF that's what we're looking for, right? VF is what we're looking for. Okay, so let's pull out the calculator, do this one as a group to make sure that we can do this correctly on our calculator. Let's say 1,500 times 20. I'm going to press enter, plus bracket 1,700 times negative 21 and the bracket. And then I'm going to take the 3,200 over by dividing. Negative 1.78, negative 1.8. So what is that telling me here? Yeah, they head off to the south at 1.8 meters per second after the collision. Make sense? You can imagine where the applications of this might be, right? Like if you're a traffic reconstruction expert for the police, or traffic accident reconstruction expert for the police, you go to an accident scene, you don't want to find the final velocity of these cars, the velocity right after the collision. What do you want to find? Well, you do pretty much the same thing, except instead of solving for VF, you solve for VI. Let's see how fast the car was going before it collided. Right? Let's see if he was speeding or not. Okay, let's take a look at another example here. It says a 0.006 kilogram ball moving at 3 meters per second to the north collides with another 0.006 ball traveling 2 meters per second to the south. First ball moves off at 1 to the south. It's the velocity of the second car. Second ball. The second ball immediately after the collision. All right. Let's circle this because it's south, right? Let's say M1 is 0.0060 kilograms. That's what M2 is as well. That's good news to me. Now, you guys haven't done too many of these questions, just one, in fact, so far. But does anybody want to take a guess at why I consider that good news? Those masses being the same are good news, Laura? They're going to end up canceling. Okay, you'll see why in a moment. That's going to save me some effort in calculator entry, data entry, because they end up canceling. I'm going to say V1 initial is 3 meters per second. And I'm going to say V2 initial is negative 2 meters per second. The first ball, V1F, sorry, I should have circled that one as well. V1F is negative 1 meter per second. We want to find out what V2F is. So let's analyze the system. If we want to analyze one ball or the other, it would be impulse. If we analyze the system, then it would be conservation of momentum. And notice again that we're doing it immediately after the collision, so we don't give other forces a chance to take effect. We can ensure it's an isolated system. We're going to say M1 V1I plus M2 V2I equals, what am I going to say for the final, right? Yeah, we don't want that yet. We don't want the number yet. We want the term here, term or terms. How many objects do we have after the collision? 2. So we're going to say M1 V1F plus M2 V2F. Right? And we said a minute ago that masses cancel. Why? Because they're all the same. Like, which is great news for me. Because then it becomes an addition-subtraction problem. V1I is 3. V2I is negative 2. V1F is negative 1 plus V2F. 3 minus 2 is 1. Add 1 to that. When we bring it over to the other side, it becomes 2. And V2F is positive 2. What I'd like you to do right now is take a look at worksheet number 3. There's a number of questions on this worksheet. Goes up to number 7. But I'm going to ask you right now for the remainder of this class just to take a look at worksheet number 3, questions 1 to 5 for now. That'll be your homework for tonight, 1 to 5.